Are you ready to learn all about vectors? Here we go. Vectors are quantities that have both magnitude and direction. So say I throw a ball at 20 feet per second straight up. That's a vector because there's my magnitude and there's my direction. But if I just say I'm driving at 30 miles per hour, that's a scalar. That's not a vector because you don't know what direction I'm driving. Okay, we can represent vectors graphically with a directed line segment, and every vector has an initial point and a terminal point, and you have to know which is which. Okay, so let's let vector u, and you notice that it's a small bold typeface letter, so that means it's a vector. And if you're just writing it by hand, then you would do u with a little arrow over it. But if you're typing, you do a small bold. Okay, so vector u is going to go from point P at 0, 0, all the way to Q, which is at 5, 3. And we draw from P out to Q, and we put an arrow at the terminal point. Now vector V, I'll do that in red, is going to go from negative 3, 2. So that's negative 3, 2. And that's point T. And W is negative 6, negative 2. So there's W. And now we always go from the initial point to the terminal point, and then we draw our arrow. Now the cool thing about vectors is that you can pick them up and move them around as long as you don't change their direction and you don't change their length. Their length is the magnitude, and the slope is their direction. Okay, so how do we calculate the magnitudes? Well, we just use the distance formula. So if I want to get the magnitude of PQ, that's what this double absolute value sign looks like. That means the magnitude from P to Q and the magnitude of vector TW. We're going to do the distance formula. So P goes from 0, 0 to 5, 3. So the magnitude of vector PQ, notice I put the initial point first and the terminal point second, is going to be the square root of 5 minus 0 squared plus 3 minus 0 squared. That's the terminal point x-coordinate minus initial point x-coordinate, terminal point y-coordinate minus initial point y-coordinate squared. And I get the square root of 25 plus 9, which is a square root of 34. That's the magnitude of PQ. All right, magnitude of vector TW. Okay, so now we are going from negative 3, 2 to negative 6, negative 2. So that's negative 3, 2, negative 6, negative 2. So that's going to be the square root of negative 6 plus 3 squared. We're subtracting negative 3 plus negative 2 minus 2 squared, which is going to give us negative 3 squared is 9, and negative 4 squared is 16. And so I get the square root of 25, which is 5. Your magnitude is always going to be positive, by the way. Okay, so you can also write vectors in component form. And if I have initial point and terminal point, then in component form, we use these kind of pointed parentheses here. And that's going to be Q1 minus P1, comma, Q2 minus P2. In other words, I subtract the terminal point coordinates minus the initial point coordinates, and I get v1, v2, which is vector v. I'll do an example so it'll be a little clearer. Okay, and then we just did the magnitude of v. Okay, now if the magnitude of v equals 1, then we call vector v a unit vector. All unit vectors have a length of 1. All right, so let's find the component form and magnitude of the vector v that has initial point 3, negative 4 and terminal point 9, 4. So vector v is going to be, now we're going to always do terminal point minus initial point. So it's going to be 9 minus 3, comma, 4 minus negative 4. And that works out to 6, comma, 8. Nope. Yes, 6, comma, 8. That's right. Now, the magnitude of vector v is going to be the square root of this squared plus this squared. And so we get the square root of 36 plus 64, which is the square root of 100, which is 10. Okay, so we use vectors because they're really easy to work with. If I want to add two vectors together, like if vector u is in component form like this, where we have u1 comma u2 and vector v is v1 comma v2, then if I want to add vector u to vector v, I just add their x components and I add their y components. I can also do what's called scalar multiplication, and k is called a scalar, just a real number. There's no direction, it's just pure magnitude. Then if I want to multiply that vector by the scalar k, I just distribute the k to the x component and to the y component. So let's do an example. Let's let vector v be 3, 5 and vector u be negative 4, 2. So 2u is going to be negative 4 times 2, which is negative 8, and 2 times 2, which is 4. Okay, u minus v, that's going to be negative 4 minus 3, and 2 minus 5. And then u plus 2v, that's going to be 3, 5 plus, whoop, I did v plus 2u I was getting ready to do, right? Okay, so what we're going to do is u, that's negative 4, 2, plus 2v, that's going to be 6, 10. And when we work that out, we get 2, 12. All right, now let's add vectors graphically. If I want to add u plus v graphically, well, u is negative 4, 2. That means if I start it at 0, 0, I'm going to go back 4 and up 2. So there's vector u. And then if I add v to it, I'm going to start at the end of vector u and plot out my vector v. So that means go 3 to the right and up 1, 2, 3, 4, 5. So here's v. Now, the vector that results from u plus v is the vector that starts at the beginning of u and goes all the way to the end of v. And that's called the resultant. So that's u plus v. Okay? All right, so I've already said that a unit vector is a vector whose magnitude is 1. And if you want to force a vector to be a unit vector, then all you need to do is divide its components by the magnitude. So a unit vector in the direction of v would be negative 3 over the magnitude of vector v, comma, 4 over the magnitude of vector v. Let's get the magnitude of vector v. That's the square root of negative 3 squared plus 4 squared, which is 9 plus 16, and the square root of 25 is 5. So a unit vector in the same direction as v is going to be negative 3/5, comma, 4/5. That's going to be going in exactly the same direction as vector v, but it's only going to have a length of 1 unit. Now we have two standard unit vectors. Vector I is a unit vector in the horizontal direction, so it's going out 1, 0. So it's going out like this. Let's see. There's one that way and one that way. So there's vector I. Vector J is going in the vertical direction, so it's going to 0, 1. So I can write any vector as a linear combination of I and j. Vector u can be rewritten as 8i plus 2j. That means I'm going 8 units horizontally and 2 units vertically. Now you can also determine the direction a vector is going by figuring out the angle that the vector makes with the positive x-axis. And if you have a vector written in component form, ai plus bj, then the angle it makes you can figure out by saying the tangent of theta is equal to b over a. Because if you think about it, if vector u is going out, let's say that that's a and that's b. Okay, it's going out horizontally a and up vertically b. Then here's theta, and remember that the tangent of theta is the opposite over the adjacent, so that means that the tangent of theta is b over a. Okay, So let's find the direction angle for this vector. Well, the tangent of theta is b over a. And we get our calculator, and it's in degree mode. So I go second tangent 7 divided by 3. And it's about 66.8 degrees. And our last example. So let's find the component form of the vector u with magnitude 6. So that's 6 units that way. And the direction angle is 60. So the problem is, what is b and what is a? Well, the cosine of 60 degrees, according to our little right triangle we just figured out there, is going to be the adjacent over the hypotenuse, which in this case is the magnitude. So it's 6 cosine 60, which is 6 times 1/2, which is 3. And the sine of 60 is the opposite over the hypotenuse. So that's b over 6. So that's 6 sine 60 equals b. And that means that b is 6 times the square root of 3 over 2, which is 3 root 3. So that means that vector u is equal to 3I plus 3 root 3j. And you can generalize that result by saying that u is equal to the magnitude of u times the cosine of theta in the I direction plus the magnitude of u times the sine of theta in the j direction. And that's pretty much all you need to know about vectors in the plane.